All right, so we're going to get started at 6:15 with the speech from. Yes, got the dean and the chair, faculty and student clubs.
Okay, ready?
We are.
Anybody online? Okay. All right. Welcome, everybody. So let's kick this thing off. I'm Kenrick Mock. I'm the interim dean for the College of Engineering. And I just like point out, I had this microphone, even though there's no speaker anywhere, because we've got an online audience. And so as we cruise around, there'll be this cart with the computer and a camera following you around. So welcome to the last of our journey into engineering events. I recognize a lot of you from previous ones, so thank you for coming to these events. So this one is all about electrical engineering, and I thought I'd add a little something different than I've been doing at the previous ones. I started out my degree as an electrical and computer engineer. So right out of high school, my major was electrical computer engineering at UC Davis, and I was really interested in signal processing. So like how you can transmit data electronically, like over a phone line or whatever, over a network. And along the way, and I'm still interested in that kind of stuff. Um, Along the way, maybe in my senior year, at the beginning of my senior year, I got a message from my advisor, and I had never seen my advisor to that point. Um, and he said, your degree is going away. You need to pick a new degree. And so they actually got rid of that degree. I'm not sure exactly why, but they had a new degree. It was electrical, it was computer science and engineering, and that was most closely related to the one I was in. So, and it was anyway, I ended up doing more of a software kind of thing. But my one little story for you is it would be good for you to, if you come here or wherever you go for college, keep in touch with your professors. If I had been going to my advising sessions, which I was supposed to do, then I would have known before my senior year that I had to switch to a different degree. On top of that, my buddies were getting these cool jobs like internships at Apple and Intel, and I was working as like a stagehand for the theater, which was fun, but these other guys were getting these jobs because they were talking to their professors and they hooked them up with all these opportunities. So talk to your professors. It's a great way to get involved and know what's going on. Okay, so we are in the EIB, the Engineering and Industry Building. So this is where most of the labs are for the College of Engineering and some faculty offices. We have another building, the Engineering and Computation Building, and that's got mostly classrooms and some other faculty offices. And we have these two buildings because we've had lots of growth over the years. We've gone from around 800 students from maybe 5 years ago to close to 1,400 students today. So we see a lot of growth both in our enrollment and research projects that we're working on. So this is the last one of our events, but I'd just like to point out that we do have other degrees in the college. And so for bachelor's degrees, we've got computer science, computer systems engineering, mechanical engineering, civil engineering, and geomatics. And then civil engineering and mechanical engineering both have graduate programs, and there's also a graduate program in project management. Our students are getting jobs at an incredible rate, and so we do a survey when students graduate, and the numbers we've been hearing back is around 3/4 of them have a job lined up by the time they graduate. And they're going to some pretty cool places, like we have a person working at NASA, SpaceX, Tesla, let's see, Intel, what am I missing? Google. So they're all over the place doing some pretty amazing things. So with that little bit of intro, I'd like to turn it over to Jens Monk. He is the chair of the electrical engineering department. So he'll say a little more about EE. And basically the rest of the event is we'll lead you on a tour through these laboratories one floor up.
Thank you, Kenrick. The one thing I can promise all of you is if you start here in electrical engineering, we'll have an electrical engineering degree when you're done. You're not going to have to switch majors. I didn't know about Kenrick's unfortunate experience at UC Davis, but yeah, I've been here 18 years. I started out teaching physics here for a year. And when I started, we didn't have an electrical engineering degree. We had what was called a 2+2 program, where we were teaching the first 2 years of the EE curriculum and then sending the students on to UAF. And after, I think about 3 years, we worked on getting our own major. And one of the requirements to getting accredited is having graduates in that major. So upon having our very first graduate, we applied for accreditation, got it. Our most recent accreditation process was finished a couple years ago, clean bill of health for 6 years. A very strong review, by the way. We currently have 6 faculty members in my department, including myself. We have 2 of our new young faculty who are experts in the area of power, Professor Hidari and Professor Abu Hussein over there in the corner. So if you come here, you'll definitely get to know those 2. You know, like I said, there's only 6 of us. So what I want to do today is just tour some labs, just to kind of give you an idea of some of the things that we do in power here at UAA. Our faculty members cover the area of power, control systems, which is very related to robotics. We have 2 faculty members in electromagnetics, myself and Professor Peterson, and Professor Meixel is our telecom guy. So we have a really nice range of expertise, particularly as it relates to jobs here in Alaska. Our graduates, particularly this year, have just been getting snapped up faster than we can crank them out. We do track where everybody is, and to my knowledge, I don't think anybody is looking for work. The other thing that we might want to measure ourselves, how do we compare against other schools? There's an engineering exam called the FE exam that you take your senior year. And the national average, the pass rate for accredited schools is 72%. We're about 93 or 94%. We don't teach to the test. That's just how they do. So I'm imagining that's at least a standard deviation or 2 better than the average. So we pride ourselves on doing a really good job with instruction at this university. I mean, you really get to know your professors. We care about you. You're in a beautiful place. We're an incredible value. if you've shopped other places. Your parents might care more about this than you. But the, um, the state of Alaska has historically been pretty generous, and education is still affordable in the state of Alaska. So having said that, do you have any questions for myself or any of our faculty, Dean Mock? Otherwise, we can start our tour. Okay, how many of you guys have been with other tours earlier with mechanical engineering or? Okay, were they all this week? Okay, wow. Okay, so this this is a lot of time for you guys. So I appreciate you guys coming. We really do. So thank you.
So if you are excited about the career in the current industry, renewable energy, utilities, like working in a power utility, transmission, or distribution company, this is the major that you want to learn. So as you can see, our lab is equipped. Some of the equipment that you're supposed to see today are not here for next year. So the benches that you are seeing everywhere on the outside for that, transformers, power transformers, you will use for lab training. For now, this thing is for power electronic training. This is what you use to interface renewable energy with electric grid, right? So you use something called electronics. And this over here, this is a real-time digital simulator. This records like 170 frame. This helps you model a whole electrical grid inside the PC and run it at real time. Currently, our students are testing an actual grid with relays, these relays. If you have a short circuit or a fault in the system, these relays hold took the breakers in the system and put it in. So I know you don't care, and you don't know what I'm talking about, but in general, like there is a whole value to this. So these guys donated to us, to one of our students, and those was like 28K. So without this, you wouldn't have the ability to test such relays. Once you get to junior or senior years, you that you have this facility, and not many universities have real-time power systems. What else can I tell you about? As far as research and how, the fact that we have 6 professors and 2 of us are power engineers, this should tell you something about the importance of power engineering. So, like, if you are on the fence of deciding between electrical engineering or other engineering majors, like, how many of you are interested in, let's say, civil engineering? Those of you who can the choice. Maybe you don't want to ruin your career, right? So, electrical engineering is the center of technology, right? We are the future. Like civil engineering seems to develop at some point. We are already at 200 years old, field. So this is the place where you want to go. We have like direct communication with our student. I actually believe in every one of our faculty. I believe in them. They're very good. They're very friendly with our students, and you can ask the students around. And if not for anything, it's for that guy. He's the best guy. None of that guy more than the other. That's why you should like. And it's good. So, if you have any question, I'm not sure what I can explain more because you basically English, but if you have any question about the degree, about the key requirements for the degree, like the general courses, chemistry, physics, I have those are something that question. And then give me a quick because parents will get more. Any parents here? Anything? Yeah. So, do you have any questions?
How many students do you have in the electrical?
In a class, I would say the maximum I would see 30. But we would have something about 10 in the electric. So, yeah. So how many would
over 100. I think we've graduated 150 or so.
Okay.
And it's really interesting because, now there's been 10 years and we're starting to see them move up. I mean, a lot of them are professional engineers now.
We have about 6 in our company.
Oh, okay.
So, yeah.
So,
We're
trying to crank them out, but we're making sure that the quality is there. Because we want to make sure our reputation is. Ahmed, did you mention that you can get killed in the slab?
Yeah. We try our best not to do so, right? So, really, like, this is one aspect of it. Hurt yourself, but I emphasize that the student has to do everything by himself. So not in like actual circuits, but you will do the connection. You will power the circuit by yourself. I will just be powering around. So, like the emphasis is on hands-on, not on simulation. And you have total freedom to do whatever best on project you want. So you can do an internship outside. It can still count as capstone project. Good. Questions? We're just waiting for this to end.
I got a question.
Yeah, but so here's the thing, when I talk to mechanical engineering students, they're really interested about power. But why did we go to power? And ask them. They always have this impression at first year that we're only dealing with electronics, which something doesn't interest me at all. So it doesn't always have to be like electronics. You can do either electronics, the small ones, or you can do also like power electronics, which is like really the we have a wide variety of circuit size, I would say, and we like nano electronics and can go up to megawatts. So whatever you're interested in.
Earlier you mentioned capstone projects. Can you give some examples of capstone projects that happen out of electrical?
Yeah, sure. So Mohammed can tell you a little bit. So
what is that? Am I jumping ahead to the wrong line?
So she wants to give an example of a capstone project that was electrical engineering.
Yeah.
If you could get close to the microphone, because they can't hear you online if you're going to talk for a little while.
Maybe I can speak loudly. Well,
It's the microphone's being worn, so you can just pass it over. There we go. Thank you.
Can you hear me? Yes, sir. Online, yeah. Okay. So I'm also a power engineer, and I think it's a very exciting time to be an electrical engineer. Let's talk about power system. You know, we do research on smart cities, smart grid, power and energy system. You know, power and energy system has been there for a long time. But now that system is witnessing a transformation. Electrical vehicles are coming to the picture, renewables, and electrification of heat. So these are all coming, and that's why I think it's very important time to be an electrical engineer, specifically a power engineer. So that's why we are very excited about this. So what was the question?
We want to know about capstone projects.
Yeah, we do a lot of projects. One of the projects that we are currently working on is solar system. You know, solar is coming to Alaska, and the thing is, we don't know how much solar are being added to the system. So we need to add some data loggers to collect some data and see like how much generation are going to be added to the system, and how that is going to affect the power and energy system. How are we going to operate the system in a reliable way? So these are all the questions that we are trying to answer. It's one of the capstone projects that we are working on. And the other project that we are working on is interdependency of power and energy systems with other networks like transportation, water. And we are going to see like how they are connected. You know, more in particular in Alaska, we have a lot of isolated grids. So we have microgrids. We would like to know how we can operate that, how we can help, let's say, rural Alaska, if they are not connected to the main grid. So how can we add wind turbines? How can we add a solar system? Trying to make them self-sustain. So these are the projects that we are working on, and hopefully we can get help from you in future. I'm working on these projects, real projects. Yeah. Thank you.
This is an electrical resistor. It's a regular one. This is an electrical resistor. I'll show you what a normal resistor looks like. I mean, Matt mentioned things scale up in power.
Yeah, you might want to give that to Yan.
Want the microphone? Are you gonna
Oh,
talk about it?
no, I was just going to show this.
Thank you. All right.
Do you all explore, solving issues using a multidisciplinary approach? Last night we were seeing water flow through, and I don't know what it was called, but it was I guess it was generating electricity.
Upstairs in the last lecture.
Right. How many students were here last night?
Civil engineering.
So you saw what I saw, right? And so I was just wondering, do you ever in projects ever team up with other engineers of other disciplines to solve issues, to explore? Can you talk a little bit about that?
Yeah,
I think that's
actually,
pretty exciting.
The second project that I just talked to you about is interconnection of water and power. We can generate power out of the water system. It's not only about those dams, those huge dams. It's about like generating power out of water distribution network. We can install some turbines and generate power, and also water system requires some energy for its pumps. So that energy, can be generated through renewables, and then we can operate those pumps. So we see how they are connected. So all these networks are interconnected. So that is the second project that I just talked to you about. So we are trying to see like how they are connected and how we can get the most out of these two interconnected networks. Yeah. Let me know if you have more questions. Yeah.
Other investor, how many owns this? Not very many, actually. Yeah, it's not very many. It might be one or two. I was using, I think, did I buy this for a project?
When I came here twice.
Okay. So, and it throws off a lot of heat, because we were putting some serious current. But anyway, yeah, this is typically, they have diodes the size of my arm, right? Everything just scaled up in power. It doesn't look like a little circuit. And everything in power will be over, right?
Yeah, if
I mean,
you
it's
throw it
scary.
at someone, it will kill them.
Well, yeah, I mean, I guess this bludgeons somebody. So. One or two ohms, like really low resistance. Yeah, so. Hey, you put a little voltage across this, you're gonna get a lot of current through it. Hot, which is why it has fins. I mean, part of this design is dissipate. It's really hot. I don't remember why I bought this. I was using it for, I was doing a transformer experiment over there, and I wanted to put an electrical load on the transformer. That transformer was part of a sidewalk heating project, and I was curious what the losses of the transformer were. So I needed a load that was about loaded. I believe it was carbon fiber tape. We use tape sidewalks so we don't have to shovel it and the snow melts automatically. It was a different way to do a snow melting system. There were problems because are there any civil engineers in there? Because it's civil engineering design. So we have to figure out what the problem. This isn't on paper.
Absolutely.
Yes, it is.
Forget that I said that.
No. It's another example of collaboration right there, right? Civil engineer, electrical
Yeah,
engineer.
the lab we're going to take you after the next lab is a robotics lab, which is really probably the most collaborative area. And you guys have probably seen robotics lab.
They're on the team.
Oh, yeah, okay, all right. So, you guys have any more questions? I feel like I didn't hand this off to the power.
Well, the time is about right if we want to change locations.
While you guys are talking, just talk right into the mic. Oh, okay. No, we're not gonna talk. I'll deliver it to her. Oh my gosh, I need
Is Cheryl going to do it?
Yeah, just change this. They actually need
Do you know that microphone's not amplification, just for streaming? They tell you that. So it's not, you're not going to hear yourself really loud on that. It's just for online. So keep talking into it. It'll sound like it's dead.
It's on, right? Okay.
Cool.
No, they can hear me. I know. That'd be terrible. All right. Are we all ready? Okay. Later, when we're done with that, well, yeah.
Do you want me to introduce you?
Yeah, you should, and then you should introduce Austin.
No. Okay. This is awesome. Oh, okay. So, is this mic hot?
Yeah.
Okay. So, you guys can all hear me, right? This is kind of our main electrical engineering lab where we do a lot of the more typical things dealing with electrical circuits. So I think there are at least 4 or 5 different classes that utilize this lab. So starting from our very first circuits class, we have 2 basic circuits classes. We have an electronics class. We have a digital circuits class. But this is a very busy utilized lab, as you can probably tell. So I'm going to introduce Mariana Lugo, okay, who's a member of the Society of Women Engineers, and she's going to talk a little bit about that organization. And then I'll introduce Austin Paulus, who is going to talk about IEEE. Is that right?
Yeah.
Did you know you were going to talk about that, Austin? Okay, just a little bit. And we should all congratulate Austin. He, can I say, you got accepted to Colorado School of Mines for his master's degree. So kudos to him. So.
All right. Hey guys, well, I'm Mariana and I'm from the Society of Women Engineers chapter here at UAA. Cheryl, can you? Okay. Yeah, so the Society of Women Engineers is a non-for-profit educational and service organization. So we do a lot of community service. That's our main goal here, but also to empower women in engineering. There's not a whole lot of us, so it's cool for us to join together and just help each other out. The Society of Women Engineers was founded in 1950, and we have chapters all over the nation. Cheryl, can you? Okay, so here at UAA, we do mostly community service, and we just mentor each other. In our meetings, we usually have guest speakers, and we also have some major events like the Women in Engineering Night, which is just a night where we have a keynote speaker that is a woman engineer, and just networking events, which is really awesome. I mean, most of you guys, you're most guys, but you can also come and also join SWE. As long as you support women in engineering, you're welcome here. Also, we do the 9 in the Spine, which is an event here at UAA. We do a whole. This year was really fun. We did like a little road with a moose, and you couldn't hit the moose to get. It was really cool. And then we do the K through 12 outreach, which is why you guys are here today, so we can inspire you and hopefully come here to UAA and be part of the Society of Women Engineers. Thank you, guys. Good. Thank you. And now we have Austin.
This doesn't work. It does? Okay. So hello everyone, I'm Austin Pavlis. I am the secretary for the UAA chapter of IEEE, which is the International Society of Electrical and Electronics Engineers. It is the professional society for electrical engineers and related disciplines. Our student chapter here on campus, we host once monthly meetings where we bring in professionals from around Anchorage who come and talk to us about professions and what possible paths after college. And a lot of times those people are offering internships, which is why we bring them in. That's pretty much all I have to say about IEEE.
We can just look at the well, not really, but you guys can look here. We have our cool stuff here, so you guys can gather here. And Austin and Cheryl are gonna show you everything.
Okay.
All right, so it looks like we have some cool demos set up over here. Austin and Cheryl are going to show you these demonstrations. And Austin and Cheryl, can you guys pass the microphone? Oh,
You're first.
I do not.
No. Wait, you can do this. Go for it. Why are you guys doing this to me? Okay, guys. So this is a lab we did in our microelectronics class. Is a rectifier, and we have cool blinking lights, which we think is pretty cool. Yeah, that's it for that. Well, we have some diodes, and we just input some voltage, and there we have our cool blinking lights. Here you go. They are pretty cool, right? Yeah.
Yeah. So that screen right there. Why is it displaying a sinusoidal wave?
Which one? Oh yeah, that's her input. Good. Yeah.
So the next thing we have going on over here, this is just a couple basic logic gates we have wired up. We use these gates quite a bit in one of the classes, computer hardware concepts here on campus. Basically, there's different logic gates that we use, and you'll wire up an input, 2 inputs into each logic gate, and then an output, which will output over here to the LEDs, and you're able to control the inputs from these switches on this side. And then based on the combination of the switches, you can control what your outputs will be. We have 4 different logic gates wired up here. That's about it. If you guys want to come and hit switches and see what happens. Yeah. And then I guess over here, this is one of the cooler things. This is a DC motor or generator. We are inputting a DC voltage. Actually, I guess this is probably an AC generator. Yep. So we have a negative voltage on this side and a positive voltage going in here, and then it is spinning this rotor. And then you can see it is reading back in the voltage that it's producing into this meter. I think natively we only have 5 volts, plus or minus 5 volts inputted onto the motor, but it is obviously reading out between 5 and 15 or 16 volts.
I don't know anything about this. I just know this stuff.
This is just a cool plasma ball. Yeah. Yeah, anyone can go and touch anything they want. You're not going to break anything. It's okay if you touch. Go for it.
That will get hot if your hand is on it for too long. Should we turn the lights on? They're playing with the cool lights. Okay. Should we turn the light on, or is it okay lighting?
Well, it doesn't matter.
Oh.
Well, yeah.
It doesn't matter. That's an excellent point. We could ask them to clear up. Could we actually, guys, for online people, do you mind letting a little window for them, let them feel like they're here a little bit? Thanks. Does that help at all?
Yeah.
Okay, cool. Thanks. That way they can feel like they're part of the group.
Yeah.
I do have. Look at that. I'm interested. Look at his screen. Yeah, he is. Oh, nice.
I mean, we're what, 30 minutes on the schedule? So who's in charge of this setup here? Like, is that something that's going to be, or is that a general one? You found it in the closet. You found it in the closet? No way.
And it looked like fun, so we pulled it out.
I am so glad you did. So I've been for the last year and a half really cool electrical demonstrations.
This is always a hit.
You hear that tone of voice? What do you want, Josh?
We did not have any tonight.
You hear that? Hey, Vicky. That's always followed by a request.
Yeah, totally.
It totally looks like it. Like the lights are out and like, you know, strobe lights going. All right. Let's break my mic there. So you're speaking?
Yes. Oh man, this is fancy.
Yeah. Let's see this. That's all right. You can run it up your jacket if you need.
Yeah. Let's hear that.
Yeah, that's right. Yeah, next time we'll have an amp so it doesn't.
Feel fancy now. I guess. As set as I'm ever going to be. Yeah, so as the name implies, we do robotics here. We build robots. We started as a club 3 years ago now, just over 3 years ago. And it was initially 4 students, or 6 students, we got together and we were like, hey, we should build robots because we did it in high school, which has kind of, there's actually high school robotics here as well, which is kind of cool. Something that's developed in the past year. But so basically we got together, we started a club, and over the past couple of years, we've seen over 100 students come through the club. Right now we have maybe 15 or so really dedicated students. And so that right there is, we deemed Iceberg 1. That was our first generation Mars-style rover. We have Iceberg 2, which is just like a CAD design, and then we have Iceberg 3. This is what we're currently working on. Iceberg 3 as well as Iceberg 3. And I'm sure there's parts over there as well. Basically, Iceberg, it's in the process of being built. We finished it, and then for a design review, and then took it apart, and now we're getting it back together. So thus why nothing actually is moving here. So the competition we're entering into is called the University Rover Challenge. It's essentially, if you were to imagine maybe, I don't know, 20, 30 years in the future, we've sent robots to Mars, and now we send people to Mars. What does that interaction look like? How do the robots and the people interact? And so this competition is meant to simulate that. So it takes place down in the middle of nowhere in Hanksville, Utah. It is, yeah, literally the middle of nowhere. It's just desert and like nothing. And so there's 4 main tasks. There's an extreme retrieval and delivery. That's essentially, you drive up to 1 kilometer away from your base station. All of this is, we're using an Xbox controller to drive the thing. We have essentially webcams that are streaming video to a base station. And so the controllers are back. They don't know, they can't actually see the rover, but they have video streams. And so the extreme retrieval, you drive up to 1 kilometer away, you pick up like objects, tools, tool chest, water bottle, and you take them to different locations. You're essentially helping out astronauts in distress, which are spacesuits that just lay on the ground and are inanimate. The autonomous traversal, I always like comparing this to Tesla. For those who know who Tesla is, the autonomous driving cars, essentially, except this is the dumbed down version, the version that doesn't cost millions of dollars. Essentially, we're told, here's a GPS location, drive to that, and then find a tennis ball. So right now we have I don't know where it is, but it's a stereoscopic camera. It's essentially 2 cameras that are positioned a certain distance apart, and then you can create a 3D map in front of you. And so we use that to generate a terrain map, so we don't run into a rock or fall off a cliff or whatever. And then we use some algorithms to actually find the tennis balls, which is surprisingly difficult because it's, orange desert and a yellow tennis ball. They're fairly similar. So that's autonomous traversal. Equipment servicing, you have this essentially a panel where you flip switches, press buttons, type on a keyboard. You have to pick up or use a screwdriver to open and close drawers, and essentially it's the hand part of the rover competition. So how fine of control can you get? And then the science cache task is actually a really cool mission where you have to drill into the soil, pick up a soil sample, and then run onboard scientific procedures. I don't know that stuff, so I can't really talk about this one too much. We have a chemistry, or is it biology major, and like a somebody who used to do environmental engineering or something like that, who are working on it. They have long, big words, scientific words. I don't know any of that stuff. So essentially, though, it's you take a soil sample, run a bunch of procedures, and the goal is there life, or can the soil like support life? And so there are certain molecules we're looking for and signs and stuff. And you look at the environment at the stratigraphic profile to learn about the geology and stuff. And so those are the 4 tasks. Like I said, these are the rovers that we've built so far. That one, well, the first 2 years, there's a cutoff point in March, so you have to submit a design review. And both years we missed the cutoff by like 1%. We were in the 1% out of the top 36 teams out of about 100. This year we made it in. I don't know where we ranked in those yet, but we made it in. That's the big news. And so we will actually be able to compete this May, June in the competition. So right now we're kind of in a frenzy trying to put everything back together so that then we can test, and then we still have to build the science platform. And yeah. I mean, that's kind of my spiel here about the club in general. Yeah.
How many hours a week do you guys usually put down?
So that's last year I actually tracked my hours, and it was about it was anywhere from about 10 on average, and then during the, like, when we had to submit our design review, it went up to like 40 hours a week. So and that was for a couple of weeks, and then it dies back down. So something we are trying to, I've been hinting at Dr. Monk, is we want this to turn into a class so you can actually get credit. Right now it's just, you know, for the heck of it. We're doing it because it's really cool stuff. We're here promoting electrical engineering, but this is a project clearly that is not just electronics. There's a lot of mechanical design that goes in. In here is the electronic stuff. And then that autonomous traversal part, in case you didn't guess it, there's lots of programming as well. So, you know, this project is essentially geared to force collaboration, because that's what you're going to be doing in the workplace. So it's a really great, like, stepping stone towards getting a job. And a lot of the students in the club actually get jobs. The one who got a job at Intel, he went through this. He's now at NVIDIA. Just, you know, tossing that out there. Yeah. Oh, we also have a guy who's at Microsoft now. So, you know, small names. Yeah. Other questions? Okay. About the lab. This year we're like, so we had a lab over in the ECB the first year, then we got moved in here last year, and then we got about $45,000 grant from the Information Technology Council on campus. So we've been able to start decking this place out with really cool tools, because it used to be there was a machine shop that we had to source, like, all of these parts. They were water jetted. These things were water jetted. A lot of the machining used to be over in the machine shop, which means we have to essentially wait on the machinist. It takes longer to build something. So we're bringing tools into here, not only for this project, but also for, like, FRC, the high school robotics team. Several of you are here. I feel like I'm rambling to you, but because you've seen this all before. But yeah, so there's FRC, and eventually we'd like to actually potentially allow other projects to happen in here. If somebody, say, was really into drones, maybe we could start a drone or get into a drone competition, or underwater vehicles, or whatever it might be. This is, as the name of the room implies, it's the Robotics Innovation Lab. And so that's kind of what we're all about, is just like promoting that sort of thing. More stuff about the lab. Over there, there's 3D printers, and something that's really cool is because we're doing electrical stuff here, PCB mill. So essentially that allows you to take, well, I should pull it up on my computer first. It's essentially a circuit design, and then you can turn that into a board design, and then turn it into a physical design. And then we have the PCB mill, so we can actually mill it out from something that looks like this to, well, this has stuff soldered to it, but if you want to check it out, it essentially allows us to get rid of all the wires, or a lot of the wires, because those are a pain. They, disconnect and stuff. And so this allows us to put everything onto just a piece of metal. Yeah. The mill, about $3,500 plus materials. Yeah. I mean, you guys have access to the lab, and the software is as easy as, once you make the board design, you just put it into the software, and you go over, plug it into the PCB mill, and like click a couple of buttons, and it just starts milling. And you have to swap out the bits every so often. It's really easy. So, yeah. If you guys want to work on board design, yeah, we have Tyler. He's done a lot of this stuff. So, yeah. Okay, one more selling point is, I could probably keep going on with the selling points, but you have this fee every year that is for printing supplies. Somehow, at least I know, I always ran through that entire fee, and then you can't print here on campus, which is a pain. We have a printer and like reams of paper. You can print whatever you want. We have a nice little router so that we can, have like consistent download speeds. We have study material. We have, there's something called the Fundamentals of Engineering exam, and that is a certification. We have study material for that. So, besides having the cool tools, having the cool project, having like the best minds here, you also have just like basic useful stuff. So, and the only way you get access to the lab is if you're part of the club. So, yeah, that's, so there's the, like I said, there's the interdisciplinary aspect of this, the mechanical, electrical, everybody working together because of jobs. Of course, that's why you're coming to college. I assume that you're coming to college so you can get like a better job and, do something you want and make more money. And so that's an advantage of clubs, especially, I know especially like the national institutions and like IEEE and stuff like that, especially they have a lot of, what would you call them? People from the industry, yes, who come in, and so you get to network. You get the same thing with something like robotics. We've had, well, I actually got I have an internship I got through robotics, and so there have been several people like that. So it's a really great networking opportunity, and also like when you're in the workplace, you don't want to like be screwing up all the time because it costs money and might make, you might get fired. Here, it doesn't matter nearly as much. And so that's a really cool thing here is you get to like do stuff hands-on. If it messes up, then you're like, okay, back to the drawing board, let's restart. And everybody's like, cool, who cares? Move on. And so you won't lose a job or get fired or anything. So. This is the same one as the other one that went around. It's just like a slightly updated version, or older version, sorry. Yeah.
Let's do it. Thank you so much.
Yeah.
They're not part of it, no.
Thank you. Are we all here yet? How are you guys holding up? Good. I mean, how do you get you a long day at school, then coming here? And I appreciate especially that this is probably the second or third time some of you guys have come through. So hopefully this is the most interesting and illuminating of all of them. It's not a competition. Yeah, we were. So this is the electromagnetics lab, and I mentioned that two of our faculty have backgrounds in electromagnetics, myself and Professor Peterson. So electromagnetics deals with maybe designing antennas, calculating how electromagnetic waves bounce off of things. In this case, we have some students who are actually building a Doppler radar where they're going to be able to tell how fast something is moving with respect, well, to this moving target here. So they've pretty much built everything, including these two horn antennas. So they're sending out a really high frequency wave. It's bouncing off, well, everything in this room. And if something happens to be moving, what happens is if it's moving towards the target, the frequency that the receive antenna is going to pick up is going to be a little bit higher. Not a lot higher, but a little bit higher. So what we do is we send out a known frequency, we measure what comes back, and we do what's called we demultiplex it. So what we're doing is kind of comparing that frequency to the one we sent and measuring very small differences in what comes back. So it turns out that my electrostatic speaker here is a really good electromagnetic reflector because it has a big metal panel here. So as I move this speaker back and forth, if you guys look at this screen here, which isn't really doing anything right now, what you're going to see is this really nice periodic signal. It's not quite a sinusoid, but it's close. So I'm going to put the speaker down. You also see if I move in front of it, it's kind of getting reflections from me. And so this is basically a radar system. So, what surprised us most of all is how well this thing's working. So not only that it's working, but it's working well. And it involves some microwave circuitry. So we're dealing with really high frequencies. So something that a sinusoid that's not oscillating 60 times a second like your AC does, but 2.4 billion times a second, 2.4 times 10 to the ninth. We can also sweep the frequency from 2.3 to 2.5 or whatever. And our next step in this radar is going to be to design a pulse radar system where we're sending out an echo and we can measure reflections from stationary targets. So this is like stepping up, raising the bar a bit. What we want to do then is actually process the data that we get by taking the radar system, scanning it in front of a target, taking that image and kind of doing what's called synthetic aperture radar processing and processing a much clearer image of what the target is. So try to do some image processing, or I should say image resolution, trying to determine what the target is. Was that Austin? Austin's leaving the end of this semester. Yeah. But can I say you probably have the record for getting through here in the shortest amount of time? 3 years. Pretty good. So do you guys have any questions about this? This project here involves a lot of electromagnetics, antennas, and we have a full year of electromagnetics at UAA, which is a little bit unusual. That's a lot of electromagnetics. It's a really important area. Not everybody agrees with that, but we think so. And we also have a separate course in antennas. So you actually learn how different antennas radiate, including horn antennas, antenna arrays, scanning antenna arrays. So you really learn we do a lot of calculation of radiation patterns. How do these things radiate energy into space? And another example of an antenna, well, kind of an acoustic antenna, is this thing here, which is an electrostatic speaker. So this isn't an electromagnetic wave. It's actually going to be an acoustic wave, but a lot of the principles that you need to understand how antennas work applies to this right here. And if you guys are familiar with electrostatic speakers, you're probably not. Has anybody ever heard of them? So, I mean, a speaker is just something that's going to take electrical energy and convert it into acoustical energy. So it's going to take that electrical energy and convert it into a mechanical wave that's going to transmit a pressure wave. And you guys have seen your normal speakers, or like that 9 or 10-inch cone down there you guys recognize as a woofer, if you guys are familiar with that term. Generally speaking, you have a really small dome-shaped thing that generates the high frequency tones in a speaker. In this speaker, this is doing the high frequencies and the mids. So the reason this thing doesn't generate the high frequencies is because it has too much mass. It can't move that fast. This thing is basically a piece of really thin, incredibly light mylar that's sandwiched between two perforated metal panels. And somehow we're going to get this thing to move. We're going to get it to create sound. So we have to do a couple things. The first thing we do is take that mylar and we're going to paint a really, it's a very high resistivity coating on it, but we want electrical charge to spread out on the mylar. We're going to put a 2000 volt static charge on the mylar. You can't hurt yourself. This isn't a power lab. This is like, you walk across the carpet and get a static shock. It's that kind of thing. Then we also take, well, the first thing you do in a speaker is you kind of divide up where the signal goes. What part of it goes to the high frequencies? What part goes to the low frequencies? That requires a filter, so a basic circuit with an inductor, a capacitor, something that's going to say, oh, hey, high frequencies go this way, low frequencies go down that way. We then take the signal that's going to these and we crank up the voltage by a factor of 100. It goes to a huge step-up transformer. So big static charge in the mylar and big voltage across the two panels. As your signal is changing back and forth in polarity, what's happening is there's an electric field between these two panels. It's flipping directions. And what happens when you put a charge in an electric field? It exerts a force on it. Now we have mylar that has charge on it. So as the field is changing back and forth, it's acting like a sail in the wind, and it's causing this thing to go back and forth. Now, this thing is big compared to a little 1-inch tweeter, but it's playing the same frequencies. So something else is going to happen here. Now you think, well, little thing is going to be more directional. The sound is going to be more focused. This thing, it's going to really throw out sound everywhere. And in fact, the exact opposite is true. If something is big, and we say big, we mean big in terms of wavelength. What happens is it doesn't send out like this big spherical wave. You get constructive interference. So it's adding constructively in this direction. And if you move a little bit this way, you're like, wow, those high frequencies really drop off. So the high frequencies are the frequencies where this is like maybe several wavelengths in size. And so if you move a little bit, what happens is you get the signal from this part here and this part here actually canceling each other out. If you're right in front of them, they always add constructively. But when you get off to the side, all sorts of horrible things happen. That's what happens with these antennas. As you look at a big parabolic dish antenna, that antenna is large in terms of wavelengths. And what that means is you get really strong constructive interference in a certain direction. So even though this is just an acoustic wave and this would be an electromagnetic wave, the principles are the same. So maybe we could call this an acoustic antenna. Okay. So Professor Peterson unplugged it so we could play with his Doppler radar, but I need to hook it up again. So I'll probably need a couple minutes, but I want you guys to listen to these things. I'm going to put a chair in the sweet spot, and I want you guys to notice how different they sound when you're right in front of them where you should be versus when you're walking around the room. You'll also notice they radiate out in both directions. The other thing you'll notice is when you get really close to them, you can't tell you're close to them. Because normally if you have something, a small thing, that power is spreading out spherically and you can detect it's getting loud very quickly as you move close to it. This is if I want to call it a plane wave. And so you move close to it and you could be a foot away, an inch away, and it doesn't sound like it's changing in volume. It's interesting. So we're going to explore the space. Anyway, so if you give me a couple minutes, because that's what I'm going to take, I need to hook up my amplifier. I got to tell you guys this. We blew a fuse earlier today, and there's 4 fuses in there. And I noticed that somebody had used this as a fuse. It was probably me. Okay, this is like really bad. You know, there's a reason why fuses are there. I mean, fuses are 5-cent parts that protect $100 parts. So this was really stupid on my part. And I'm like, who the hell did that? That's not part of it. It was me. All right. I apologize for the music. Just ahead of time. Okay. I'm 58. Give me a break. All right. Okay, they're ready to go, I think. So if you guys want to take turns sitting here, don't be shy. Just I want you guys to notice how different it is, and what you're hearing is how the radiation pattern of the speakers is changing as you move out of that main beam. What you'll also notice is the low. You guys know what I mean when I say low frequencies, the low tones. They're much less directional. And when I say directional, I mean the energy is focused in a certain area. So pay attention to how the high frequencies change, but the middle and lows don't change nearly as much. So enough of me yakking. Oh, did I mention my students made these? Yeah, my students made these. And this was back when we were in the old building. I think we had the second floor of the old building. So, I mean, I've been here 18 years and the growth has been unbelievable. The facilities and the faculty that we have now, I mean, I've really seen some incredible change. We did this in my garage. Okay, that's how long ago this was. And they almost put me in the poorhouse because I would feed them on the weekends. And one of them was a power lifter. So, you know. Have you heard this before?
I'll go to the sea. I'll stay on the land till the rain comes again. I'll pack up my house. I'll stay in a motel till the wind passes through. I'll go to the sea. I'll go to the sea. I'll go.
So this is our what do you think, you guys? Did everybody can rock and roll? I was pretty gung ho about it. Yeah, you know what? That's my what I love. I don't have any. I have something even worse than that. So we're just gonna so buttons to parameters. Master volume switch. Still a lot more. And but I'm get this. Ours project way ambitious at the start too. It does sound essentially learning levitation. Turns out to use Arduino is like, wow, getting 15 different isolate C sensors to install together is not easy.
Don't you listen to me.
So has everybody had a chance? Do you guys have any questions for me or anything about the program or yeah, karaoke. Yeah. Well, if I don't have any, that's if you guys can mosey around for a while, or otherwise, yeah. No. If you can start in calculus, and you can start in the calc-based physics, you can do it in 4 years. It can be done in 3 years. I mean, somebody did it in 3 years, but he started in ordinary differential equations for his math. For we have a lot of credits. We require 131 credits. So 4.5 is 5 is more normal. It is. You can get through in 4 years if you can stay with the flow chart. Yeah, it is. The problem is people usually might have to take a math class to get into calc or whatever. A lot of them do. You might not have to. So what math are you taking? Oh, at UAA? Okay. Yeah, I think if you can, can I shut this off?